Consider two distributions, px and qx, defined over the same domain of x. For example, they could be continuous density function over the real line, or they are discrete distributions over a set of finite values. Then we can define the distance between the two distributions by the so-called Kullback-Leibler distance, which takes the following form. What this one is doing is that, well, to measure the distance between P and Q, we look at the log likelihood on the data, Px over Qx. And then we look at the averaged log likelihood. So we take expectation. Now, when we take expectation, we have to decide which distribution we're going to use over x. And so for K-out divergence, this expectation is actually taken respect to P. That means if P and Q are continuous, this expectation corresponds to an integral. And if P and Q are discrete, the expectation corresponds to a summation, where the expectations are taken respect to the distribution over the numerator of this log. So it is true K-out divergence is not symmetric, because if you switch the position of P and Q, the expression changed because P appeared twice, Q only appeared once. And nevertheless, K-out divergence is widely used in statistics and machine learning as a metric between distributions. We can show that K-out divergence is always bigger or equal to 0 and is equal to 0 if and only if the two distributions are almost identical. And so how we show the K-out divergence is always bigger or equal to 0. First, the K-out divergence between P and Q, as we described, is equal to expectation of log of this and the ratio of the two distributions. And in statistics, we have something called Youngson's inequality. It states that, well, if we're looking at the expectation of a function versus the function evaluated as the expectation, when G is convex, and it can be shown that this is always bigger than or equal to this. And the equal sign holds if and only if this G is just a simple like a linear function. And so in this case, let's check this equality. This equality is trivial. We basically flip the ratio inside the log. So now Q is on the numerator and P is in the denominator, and then we just add a minus sign in front of log. But what is minus log? Minus log looks like this. Here's 1. So log look like this. Minus log will look like this, which is a convex function. So we know the expectation of minus log is bigger or equal to a minus log evaluated as the expectation. But what is this expectation? If x is continuous, this expectation is equal to an integral of px and the qx divided by px and dx. And these two cancel each other, and then you just need to evaluate the integral of qx, because q is a density function, so this integral is equal to 1. So here then basically the lower bound is equal to minus log 1, which is 0. So we just shown that Kullback-Leibler distance, which is defined here and here, depending on x is discrete or continuous, is always bigger or equal to 0. And further, you can show that if equal to 0, that means P and Q are basically the same distribution. And if P and Q are discrete, that means Pj and Qj are all equal to each other. But if P and Q are density functions, when we are talking about density functions, the density function actually is not unique in the sense, if we have a normal density function and we normal 0, 1, we know its expression. But we can always define another function where I just take the value, let's see, at 1, just redefine the function at 1 to be any other value, finite value. And the density, it won't affect any of the integrals because we only change the value at a single location. And we can even change the value at 2 locations or any finite locations. So when x is continuous, when we say 2 distributions are the same, and to be accurate, we should say they're basically the same up to a measure 0 set, meaning the P and Q density functions take the same form except on some points, which is of measure 0. If you don't have the background in continuous random variables, just ignore that comment here. It's basically just some kind of mathematical technicality.